In this lecture, I want to talk about higher derivatives. And what do I mean by higher derivatives? Well, I mean taking more than the derivative once. So for example, if I start off with the function f, I could take the derivative of that, and I would get f prime. But I could take, if this is a function, then I could take the derivative of this as well, and I could get the second derivative if this is a function, and it should be, right? Because it's all with respect to x, right? Remember, when we take the derivative as a function, we get a function. So at each step here, I should be able to, as long as the derivative function is differentiable, I should be able to take the derivative again. And we can kind of go on ad infinitum here. Notationally, I just want to point out that after 3 primes, the convention is to just start putting a number up there in parentheses. So the fourth derivative of f, we would denote this way. I guess it just gets too cumbersome to start, You can glance and see 3 primes. Beyond that, it might be hard to tell the difference between 7 and 8 little prime marks, so we just use these this notation. So a quick example would be if f were x cubed minus x, then this is pretty straightforward derivative for us, right? Because we just use the power rule, so that's going to be 3x squared minus 1. That's the first derivative, but of course this is a function itself that we could take the derivative of, and so the first term becomes 6x, and the derivative of the negative 1 is just 0. And then I could take, again, this is a function, I could take the derivative of that, I would just get 6, and 6 is a constant function, right? And so we know that the derivative of any constant is 0. So anything after, we could keep going here, but anything after that is just going to remain 0. All right, so this is an example of how we could take. It's really not a difficult concept. We're just going to continue to take derivatives. If you can take a first derivative, then you can take a second derivative, and so on. What I would like to talk a little bit, though, is kind of what the second, focusing more maybe on the second derivative right now. We'll see more applications of this later, but I'd like to talk about kind of how we might understand what that means, or where, why would we keep doing this? Just because we can? No. So let's think about what some applications of this might be. And I'd like to start with this idea of distance, right? We could have a distance function. So this is the general, convention that distance is denoted with s. D seemed like it would make a lot more sense to me, but that's generally not the convention. Anyways, this is the distance function. And recall that if I take the derivative of distance with respect to time, in other words, how is the distance changing with respect to time? Well, that is velocity. All right? But what about velocity? If velocity changes with respect to time, how would we think of that? Well, we do that all the time. Anytime we drive or ride a bike or even walk, right? Anytime we move, our velocity is changing with respect to time. Because, well, given that we're starting at a stop, that our velocity is 0, so let's say we're driving and we need to get up to the speed limit, 55, 60, 65 miles an hour. Our velocity is changing, right? Because it starts at 0. Anytime you see the speedometer going up or down, if you think of a speedometer, right? So here's your speedometer, you have your little arrow. If that arrow is moving, then velocity is changing, right? It's changing with respect to time. If it's stuck in one place, then we would say velocity is constant, right? If you're just kind of staying maybe at 35 miles an hour, then velocity is constant. But if that is moving at all, then your velocity is changing with respect to time. So when velocity changes with respect to time, what do we call that? Well, we call that acceleration. So again, I think that's an idea that most of us are familiar with. But notice, since velocity is the derivative of distance, and acceleration is the derivative of velocity, then acceleration is the second derivative of distance with respect to time. It's the rate of change of the rate of change, right? The rate of change of the rate of change of distance with respect to time. But I think thinking about it this way hopefully gives you a way to kind of wrap your head around what that would mean. So I also want to kind of think about this graphically. So if this is our time axis, and here's our distance axis. Let's say we have a curve that kind of starts up like this, and then it curves back this way, and then for this part it just kind of goes straight. All right, so let's think about what's going on here. So notice here that if I were to draw in a tangent line, the tangent line would be positive. So if my distance is increasing with respect to time, then the slope of this tangent line is positive, which means velocity is increasing. All right, and then here, notice that's steeper, right? And I'm going to need to use another color to be able to see, but if I put another one in down here, so notice that as I move from this point to this point to this point, the slopes of these tangent lines, right? So there's the slope of the tangent line, looks fairly almost horizontal. Then it's here, then it's here. So the slope of the tangent line is my velocity, right? It's the derivative of distance. But those slopes are increasing. So that would indicate along here, when the slopes are increasing, that a of t or b prime of t is positive, right? They're increasing. The derivative, the rate of change of velocity is positive, it's increasing, okay? Now notice up here though, so let's say I put in a tangent line here, and then maybe another one here, and another one here. So in this case we see that the slopes of the tangent lines are decreasing, so that a of t, or the derivative of velocity, the way that the velocity is changing with respect to time, is decreasing. All right. Finally, along here, right, we see that since this is linear, that this is 0. You can kind of think of this as you're like this situation here. You're just staying at 35 miles an hour. Your velocity is not changing. There is no change in velocity with respect to time. So this is my acceleration. So here, what I want to point out, and let's see if I can get another color to emphasize this. Right here, when this is going this is called we call this concave up. It's like a bowl that holds water, all right? And in that case, we would say that the second derivative, right? Remember, this is the second derivative of distance, is positive, all right? Because we have these tangent lines are getting steeper. And then along, well, maybe another color, along here, where it's shaped like this, we would say that the second derivative is negative. This is concave down. Notice that this wouldn't hold water. This would dump the water out. So acceleration, or the second derivative, is negative. And then here, we've already said, if you have kind of a constant function, then the second derivative is 0. All right. We could also see that, for any linear function, right? I don't know. Let's say it was y equals 2x, right? That's a linear function, right? So the first derivative is constant, right? So that indicates that velocity is constant. The second derivative is 0. So for any linear function, the first derivative will be constant and the second derivative will be 0. So anyways, this is just some ideas that I think are useful in terms of thinking about the second derivative, because otherwise we're just kind of taking derivatives because we can. This, I think, is an application of the second derivative that can help us make sense of it. Okay, so much for introducing the idea. Let's see a couple of examples of the second derivative, or beyond. Okay, so the first one, I'm just going to do 2 examples here, and for each of them I'm going to use either a product or a quotient, so we can also get some more practice in thinking about the product and quotient rules. So if I've got, let's say, x squared plus x times x cubed plus 1, all right? So the first derivative, we use the product rule. So I could take the derivative of the first function, which is 2x plus 1, times the derivative of the second, just times the second function. Yes, I do know the product rule. So I've taken the derivative of the first function times the second function plus the first function times the derivative of the second, which is 3x squared. Of course, there's lots of ways we could have done this. I could have taken the, these could be switched. I could have taken the derivative of this one first. I could have these reversed as well, we said. So anyways, that's how I did it. There's more than one way to do that. But let's look at the second derivative here. So for the second derivative, one thing I could do certainly is I could expand this out, right? And then take the derivative again. Or I could use the product rule here and the product rule here, and that's how I'm going to do it. So we can kind of think of this as the product rule twice, for the first term and then for the second term. So here, take the product rule, take the derivative of the first function, which is just going to be 2, times the second function, x cubed, plus 1, plus the first function times the derivative of the second function, which is 3x squared. All right, so that's, just change colors to make it clear, that is, this right here is the derivative of the first part. And then for the second part, we use the product rule again. So I have the derivative of the first part, which is 2x plus 1, times the second, which is 3x squared, plus the first, which is x squared plus x, times the derivative of the second, which is 6x. So in this case, for this part, this is the application of the product rule to get that part of the derivative. So here's the second derivative. Again, it's a mess. We could clean it up, but that's not the point of this lecture. It's just looking at second derivatives, and in this case, second derivative applied using the product rule. Okay, so much for that example. Let's take a look at another one. So let's take a look at g of x equal to x over x plus 1, and let's say we want to find the slope of the tangent line. Sorry, not the slope of the tangent line. We want to find the second derivative evaluated at 1. All right. You could kind of think of this as the concavity, right? We just talked about if it's concave up or if it's concave down. So if the second derivative at 1 is positive, then we know it's concave up because our second derivative is positive. If the second derivative at 1 is negative, then we know that at that point it's concave down. All right. In terms of just trying to interpret this graphically. Okay, well, in order to get this, the first thing we need to do is we need to find the second derivative of g. And in order to find the second derivative, we need to find the first derivative. So one thing I want to point out here, this is not the same. I mean, if we want to simplify when we can, but this is not equal to x over x plus x over 1. Right? In order to put these together, I'd have to get a common denominator, which would give me something different than what I have up here. So don't do that. If you only have a single term in the denominator, then you might separate it out like I did in a previous lecture and simplify so that we can avoid the quotient rule because it's a little bit cumbersome. But in this case, there's no way around it. So let's go ahead and just get to it. All right, so quotient rule is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. The derivative of the denominator, derivative of that is 1, and that's 0, so that's also 1, over the denominator squared. Now, in this case, since we're going to take the second derivative, it would be useful to simplify a little. This simplifies pretty nicely, actually, because I just end up with x plus 1 minus x over x plus 1 squared, which is 1 over x plus 1 squared. But we don't know how to find the derivative of a function squared yet. That's called the chain rule, and we will get to that, but we don't know it yet. So I think that in order to kind of use what we know how to do right now, I'm just going to expand this out. So if I expand this, I get x squared plus 2x plus 1. All right, now I have something that I could take the derivative of. All right, Now, notice I still use the quotient rule here because 1 is a function, right? It's the constant function, just horizontal line at y equals 1. So, second derivative, I would have the denominator, x squared plus 2x plus 1 times the derivative of the numerator, which is 0, because the derivative of any constant is 0, minus the numerator, which is 1, times the derivative of the denominator, and that's going to give me 2x plus 2, and then the derivative of 1 goes to 0, so I'm left with just that, over x squared plus 2x plus 1 quantity squared. So let's simplify this a little bit, because ultimately I want to find g prime, double prime of 1. All right. Well, this is just 0, and then I can distribute that negative, so I have minus 2x minus 2 over x squared plus 2x plus 1 squared. Now let's go ahead and substitute 1. So I have negative 2 times 1 minus 2 over 1 squared plus 2 times 1 plus 1 quantity squared. Alright, so that's negative 2 minus 2, that's negative 4. And down here I have 1 plus 2 plus 1 squared. Well, that's 4 squared, so that's 16, so that's negative 1/4. So that's the second derivative of this function. Evaluated at 1, it's negative. So at this point, at x equals 1, this function right here is concave down. It's facing downward in some way. We don't know for how long. We just know that right at x equals 1, it kind of has this shape. It could, it could go back up on either side and become concave up again. But right at this point, it's concave down. And that will have some important applications when we begin to think about when functions are increasing or decreasing and that sort of thing that we'll see in later applications. All right, so the idea of higher derivatives is really not that difficult. It's just taking the derivative of a derivative. The part that I would want you to focus on in terms of thinking about what this means is this idea of acceleration, or the rate of change of the rate of change.